Okay, so in this lecture, we are going to talk about a gamma distribution. So here I will write x following a gamma distribution with the parameter alpha and beta. And then sometimes we also use a Greek letter gamma function, a Greek letter with two parameters to refer the gamma distribution. And then if we have, so this is notation for the distribution. And then we also have a gamma function where you input one parameter, and this is referring to the gamma function. Okay, so last time we talked about the support for x is greater than 0. And then we also have alpha, beta also are positive real values. Okay, and then the density function is f of x equal to x raised to the power of alpha minus 1, and then e raised to the power of negative x over beta. So we have a fraction on the power term. And then in the denominator, we have the gamma function that only input the alpha and then multiply by beta raised to the power alpha. So we have a numerator and a denominator. And then we usually refer the numerator as the kernel function. Okay. And then last time we also talked about two properties regarding the gamma function, which is the gamma function for when you input alpha plus 1, this is also equal to alpha multiplied by gamma of alpha. And then when the alpha are integer, we also have the gamma function is just equal to alpha minus 1 factorial. Okay, and then the definition for the gamma function essentially just an integral. So, which is the integral for x from 0 to infinity, and then x raised to the power of alpha minus 1, and then e raised to the power of negative x. So there's no more beta here, and then dx. So if you have an alpha and then you evaluate this integral, that will be the output from this gamma function. Okay, so let me put it again. This is a definition for the gamma function. Okay. Yeah, so this is what we have from last time. And now let's providing some more comments regarding this gamma distribution. So first of all is that let's take a look at the numerator here, which involving the x. So now let's one more notes. Let's take a look when we evaluating the integral from x equal to 0 to x equal to infinity, and then for the numerator of the gamma density. So this is the numerator or the kernel function, dx. Okay, so it's not the gamma function, it's the kernel function for the gamma distribution. And now let's take a look when we evaluating this integral. So first of all, let's set y equal to x over beta. So this is kind of like a u substitution again. Okay, once we parameterize y equal to the power or the fraction power, and then we know that x is equal to beta multiplied by y. And that is also saying dx is beta multiplied by dy. Okay, again, we are using u substitution to evaluating this integral here. Now let's continue our equation. So this is equal to, by replacing the x here by the part that we re-express. So now x is equal to beta y, and now we put the beta y raised to the power of alpha minus 1. So from here to here. And next, we have the e raised to the power of negative y. Okay. And then for dx, we need to write it as beta multiplied by dy. So we have, using the u substitution, to rewrite the integral of this kernel function. Okay, so this is the integral of the kernel function. Okay, and then we rewrite the integral by using the u substitution to calculate that in terms of the y. And then also y is equal to x over beta, so the range for y can also be obtained by plugging x, the range of x, in this equation here. So the y now also starting from 0, and then y go to infinity. So we have this integral to evaluate. And now one thing we can notice is that the beta here is a constant because the integral is with respect to y. So first of all, we have a beta raised to the power of alpha minus 1 in the front. And then the integral of y raised to the power of alpha minus 1, and then e raised to the power of negative y. And then we also have beta, but that beta is also a constant, so we can move it outside the integral. So you can see that we have alpha minus 1 copies of beta, and then another additional copy of beta. So now we can see that this part is essentially the definition for a gamma function. Okay, so here the constant part is beta multiplied by alpha, and then this is the gamma function that with the input alpha. So we notice that when you integral the kernel function, you will get the denominator. And usually this is also called the normalizing constant. So the idea here is that a proper defined probability density function, when you integrate with respect to the parameter for the range of x, it will be equal to 1. So now you can see that if we integral that, the numerator will obtain the denominator. So that means if we directly integrate the density function for the gamma distribution, then we will end up to 1. So let me write that down. If integrate a probability density function with respect to the support for x of the random variable x, this should be equal to 1. So this is kind of like the probability of all possible values. The area under the curve should be equal to 1. Okay. So now we can see that this is a properly defined probability density function. And then when we integral the density function f of x over all possible values for x, we should get 1. So this is a properly defined probability density function. Okay, So now, the next step when we introduce or talk about the probability of a new distribution, we will talk about, or we will calculate the moments. So in this case, let's take a look at this particular quantities. The kth order moment. So instead of calculating a particular, the first moment, which is the expectation, or the second moment, now let's consider a arbitrary kth moment, so which is defined by x raised to the power of k, taking the expectation. And now let's using the definition for the expectation, we can see that this is the x raised to the power of k multiplied by the probability density function of the gamma distribution. So here, let's plug in the density function that we have on the top, negative x over beta, and then a gamma function for the alpha, and then beta raised to the power of alpha dx. So this is just the definition of the expected value. So when you have the first moment, you plug in the x here. When you have the second moment, you plug in x raised to the power of 2. But here, we calculate the kth moment, so x raised to the power of k. And now let's see how we can simplify to evaluate this integral. So first of all, let's simplify or bring the constant that does not involving x outside the integral. So the things that does not involving x are the normalizing constant. Okay, so that is just a constant that does not involving x. And then now let's complete the integral. So here, let's group the x of the k and x raised to the power of alpha minus 1 together. Then we have x raised to the power of alpha plus k minus 1. And then we have e raised to the power of negative x over beta dx. So again, we are evaluating the kth moment for the gamma distribution, and this is the next step. Okay, so now you can see that on the top, it very looks like that it is a gamma, a kernel function for the distribution of x that following a gamma distribution with alpha plus k and then beta. So this is the kernel function of a random, if a random variable following that distribution, then this is the kernel function of that. So now, so again, this is the kernel function for a random variable that followed this particular gamma distribution, with the alpha parameter now is alpha plus k, and then the beta parameter is beta. So what we can do here is to introduce a new normalizing constant in the following way. Okay, so let's continue, and then we have the constant that is the denominator of the density function from the x of alpha k, alpha and beta. Okay, and now let's introduce one more normalizing constant. Okay, so I'm going to introduce in a way with alpha plus k, and then beta multiplied by raised to the power of alpha plus k, and then divided by the same thing. So if we are multiplying and dividing by the same thing, it does not alternate the quantity. So this is essentially just a 1. So we are introducing a factor of 1. But this 1 is expressed as a fraction. and then continue the integral. Okay, so now I'm claiming that this equation still holds because we are just introducing a factor of 1, but expressed in the following fraction form. And now let's move the things around. We will have 1 over the gamma function, beta alpha. So this is coming from the denominator from the definition. And now let's keep the numerator of this fraction outside. But now bring the denominator into the integral. So we have x of alpha plus k minus 1, and then e of x over beta divided by gamma of alpha plus k, and then beta raised to the power of alpha plus k dx. Okay, so now you will notice that by introducing a factor of 1, it does not alter the quantities. But when we leave the numerator outside the integral but the denominator inside the integral, we essentially construct a probability density function of x that follow a gamma distribution alpha plus k and then beta. So again, the formulations inside the integral now is the probability density function of x that follow a gamma distribution of alpha plus k and with parameter beta. Okay, so what we started with is that we want to calculate the kth moment of the gamma distribution of x following a gamma distribution alpha beta. But now, by introducing a factor of 1 by construction, now inside the integral is the probability density function of x following a gamma distribution. This is your new parameters. Okay. However, as we mentioned before, for any properly defined probability density function, when you take the integral with respect to d of x, then it should integrate to 1. So the whole thing here inside the integral will just go to 1. So now let's continue our equation. We have 1 over gamma of alpha beta alpha multiplying by the numerator that we introduced, beta alpha plus k. But here, the integral, there's no need to evaluate that because everything just equal to 1. That is due to a properly defined probability density function. Okay, so again, we show that when we integral the kernel function, which is the numerator, we obtain the denominator. So that formula in form of the fraction or the density function of the gamma is a properly defined, and then it can integrate to 1. Now we want to evaluate the kth moment by introducing another x of k. And then by rearranging the terms, introducing a factor of 1, we construct a new probability density function. And that integral should also be evaluated to 1. And then that means the kth moment is equal to the following. We can also simplify to have a gamma alpha plus k. Beta raised to the power of k. So this is the kth moment. So for any arbitrary k moment, of the x that follow the gamma distribution of alpha beta. Okay, it's just that we are interested in the kth moment of x that follow parameter gamma with parameter alpha beta. But throughout the process, we need to construct a probability density function for gamma distribution that with parameter alpha plus k and beta. But we notice that that is equal to integrate to 1, then it reduced to this form. And then we can further simplify that. Okay, so now we have a formula for an arbitrary kth moment for the gamma distribution. Now, if we want to evaluate the first moment, all we need to do is just set k to 1. Then we will have gamma of alpha plus 1 and the gamma of alpha multiplied by beta raised to the power of 1. Okay, and then earlier we mentioned that the property for a gamma function is that gamma function of alpha plus 1 is equal to alpha multiplied by gamma function of alpha divided by the denominator multiplied by beta. And that means the first moment of the gamma distribution is equal to alpha beta. Okay, so what we've done so far is that we derive the a formula for the arbitrary kth moment. And then by setting k equal to 1, we'll be able to get the first moment. And then the second moment, we can get it by setting k equal to 2, and then using our formula again, a plus alpha plus k, so alpha plus 2, and then alpha multiplied by beta raised to the power of k, so k is 2. Okay, so now let's simplify the numerator. So the gamma function of alpha plus 1, alpha plus 2 is equal to alpha plus a 1, and then multiply another plus another 1. So alpha plus 1 is alpha plus 2 is equal to alpha plus 1, and then plus another 1. Okay, and then the denominator stay the same. Beta raised to the power of 2. Okay, and then if you consider the alpha plus 1 as alpha star, then the numerator is a gamma function of alpha star plus 1. Then what we have is gamma function. So the way to think about how to simplify this is that you consider the alpha plus 1 as your new alpha star. So that means you have a alpha star multiply by gamma function of alpha star. So this is using the properties here. So maybe I can call this 1 and then call this 2. So here from here we are using the definition of the property of 1. And then here to here we're also using the property of 1. But that we're only working on alpha star. Okay, and then complete the rest. But like I said, we are just calling alpha plus 1 as alpha star. Then for simplifying the formula, let's bring back our definition for alpha star. we essentially have a alpha plus 1 multiplied by gamma function of alpha plus 1 divided by gamma function of alpha and then beta raised to the power of 2. We can further simplify the numerator of that function. So we have alpha plus 1, that's already a constant, and then gamma function of alpha plus 1 is just alpha multiplied by gamma function of alpha. So again, I'm using the property 1 again to further simplify that term. Then we have the following. Okay, and then beta raised to the power of 2. So now we can cancel out the gamma function from the numerator and denominator. We will have alpha plus 1 multiplied by alpha multiplied by beta raised to the power of 2. Okay. Then we will have alpha square plus alpha beta square, and then alpha squared beta squared plus alpha beta squared. And this is the second moment. So just to recap, we derive a formula for an arbitrary kth moment. And to calculate the first moment or the second moment, we just plug in k equal to 1, plug in k equal to 2. Then we'll have this form. And now we can also calculate the variance of a gamma distribution. This is just equal to the second moment minus the square of the first moment. This is equal to alpha square beta square plus alpha beta square, and then minus the square of the first moment, and the first moment is equal to alpha beta. So this is minus alpha beta altogether squared. So here we will have alpha beta squared. So we calculate the first moment by setting k equal to 1. We calculate the second moment by setting k equal to 2. And then the variance is just plug in, and then only this term remains, so that we have the variance of x, a variance of the gamma random variable. Okay, so the formula that we just derived is just a formula for an arbitrary kth moment. But now we can also calculating or get the moment generating function for a gamma random variable. Okay, so now we want to get the moment generating function of x following a gamma distribution with parameter alpha beta. Okay, so the definition, so we're going to use the definition of the moment generating function to get the formula. So we have the name for x, and then which is a function of t. By the definition, which is the expected value for e raised to the power of tx. And this is equal to the integral for e raised to the power of t multiplied by x, and then the gamma distribution, the density function. Just x raised to the power of alpha minus 1, and then beta, and then e raised to the power of negative x over beta divided by gamma function beta alpha dx. Okay, so instead of getting the formula for an arbitrary kth moment, what we're doing here is deriving the moment generating function of the gamma random variable. So instead of x raised to the power of k, now we use the definition. So we need to plug in the e raised to the power of t multiplied by x, and then evaluating this integral. Okay, so now let's simplify this integral by combining terms. So first of all, I'm going to group the e raised to the power of tx and then the e raised to the power of negative x over beta together. Okay, so integral here, x raised to the power of alpha minus 1. And then I'm grouping e tx plus, or so now this is what we have talked about, e of a multiplied by, let me put it on the top. So again, exponential of raised to the power of a multiplying by e raised to the power of b is equal to e raised to the power of a plus b. Okay, so we're going to use this to group these two exponential terms here. So we have t of x plus the power of negative x over beta. So we have a minus x over beta. So all together as the power, and then divided by the normalizing constant. So alpha, and then, so this is the integral we want to evaluate. Okay, let's further simplify one more steps. So also x from 0 to infinity. And then x alpha minus 1. And then e. So the goal here is to separate the x from the constant part. So we have the t minus, okay, let me do one more step. So t minus 1 over beta multiply by x. Okay, so I'm just pulling the common part, the common term onto the right hand side. Dx. Okay, and let's do one more change to get so now I'm going to move the negative sign for this constant to the front. So we introduce a negative. So this time we need to change the order. So 1 over beta minus a t multiplied by x. So I'm going to move the negative sign to the front to construct a formula that looks like the probability density function of a gamma distribution. That there's a negative sign, so I also want to introduce a negative sign here, and that is our new beta coefficient. Okay, so this is the new integral I want to evaluate. So again, we can use u substitution by setting u equal to 1 over beta minus t multiplying by x. And this is saying x is equal to 1 over beta minus t, and then raised to the power of negative 1. So 1 over a is equal to a raised to the power of negative 1. So I'm going to divide it by this constant part to the right hand side, and then as a denominator, so I can put it raised to the power of negative 1 and then multiply by y. Okay, so I'm doing the u substitution again. And this is saying dx is equal to the constant dy. Okay, so now we have the substitution part. Let's bring these into the integral. So continue on the equal sign. We will have the x raised to the power of alpha. So now x is equal to 1 over beta minus a t raised to the power of -1 multiplying by y. So this whole thing is what we define as x based on the u substitution. But this x also need to raise the power of alpha minus 1. So let's introduce a square bracket and then alpha minus 1. Okay, and then the other term is e raised to the power of those. But we call that part of y. So all we have is the e raised to the power of -y. Then we also have the normalizing constant. So all we need now is to replace the dx by 1 over beta minus a t raised to the power of -1, but dy. And again, if you plug in x to 0 or x to infinity, you will see that the range for y is also 0 to infinity. So we can, if you want, you can put y equal to 0 to infinity for the upper bound and lower bound. And now the trick is the same as what we did in the kernel function. So we can bring whatever is constant to the front. So we have 1 over beta minus a t, okay, minus a 1. So I'm bringing this part. So anything that does not involving the y, we can move it outside the integral. Okay, and then this part here also does not involving y. So we can bring that raised to the power of -1. And then the remaining part are the following. So this is the same trick that we did in the kernel for the first kernel function, but just slightly different constant. So we will have y raised to the power of alpha minus 1, e raised to the power of -y. And then gamma function beta raised to the power of alpha. And then dy. So next, let's simplify the constant. So first of all, we have 1 over beta minus a t. So we first raise the power of -1, and then further raise the power of alpha minus 1. And that is the same as raising the power to negative alpha minus 1. And if you want, this is 1 minus alpha. So a positive 1 minus an alpha. And then multiplying by that. Okay, so now again, you have a raised to the power of negative b, and then a raised to the power of negative c. Okay. So here x raised to the power of a multiplied by x raised to the power of b is equal to x raised to the power of a plus b for any generic x. So this is saying okay, let me put it here. Then we have that integral. That's just an very simple intermediate step. dy. Okay, so all I did here is that I bring the -1 multiplying by alpha minus 1. So we have that. But noticing that x raised to the power, so if the base is the same but the power is different, when you multiply them together, it's just by adding them. But here, this is 1 minus alpha, but when you're adding the -1, you will also have a -1. Then that will give you 1 over beta minus a t altogether just raised to the power of alpha and negative alpha. Okay. So what we did here is that the negative alpha minus 1 plus the -1 will reduce to negative alpha. And let me, maybe I can just clear the notes here. Okay, so that is how we handle the constant part in front of the integral. And now I want to multiply beta alpha divided by beta alpha. So again, I'm multiplying a 1. So it should not alternate the quantity here. And then continue. Okay, so don't do this one. So what I want to do here is the following. Okay, so I want to remove the, let me color it. So this part. Okay, so first of all, I'm going to move that outside. So if you want, you can adding a 1 here, but right now I'm just going to directly move it outside. So this is just beta alpha, but in denominator, so it's 1 over that, but now I'm writing a negative alpha. Okay, but as you can see, okay, so let me just color that. I'm just moving that part to the front, but there's something, so there's also kind of like leaving an empty space in the denominator here. What I'm doing here is just introducing a 1 raised to the power of alpha. So 1 raised to any power of alpha will just becomes a 1. It's still going to be 1. So again, the quantity does not alternate. Okay, and then dy. So let me also, I can also add a color. Okay, so 1 raised to the power of alpha is just equal to 1. So essentially we are just dividing by by dividing or multiplying by 1 here. So again, the quantity does not change. But you will realize this density here, this function here, is the probability density function of x that following a gamma distribution of alpha with the beta just equal to 1. Okay, so now I think okay. So what we have inside the integral is the probability density function of a gamma random variable that follow a gamma distribution with parameter alpha and beta is just equal to 1. Okay, so in that case, that is also a properly defined probability density function. So this part will reduce to 1. Okay, so what we have is the following. So 1 over beta minus a t raised to the power of negative alpha, beta raised to the power of negative alpha, multiplying by 1. Because this is a because the for a properly defined density function, f of x dx just equal to 1. Okay, this is like the probability of all possible events. You sum them together, you will get a probability of 1. So the things inside the integral is another probability density function for a particular alpha and beta that will integral no matter what to 1, and then we will have the following. Okay, now let me write it here. So x raised to the power of a multiplied by x raised to the power of b is the x raised to the power of a plus b. So that's what we used before. And now let's have a raised to the power of x multiplying by b raised to the power of x. This is equal to a multiplied by b altogether raised to the power of x. Okay. Yeah. So now let's take care of the first two terms. So we have 1 over beta minus a t multiplied by beta, and then all together raised to the power that is shared. Okay, so this is, I'm using the second property that x or a raised to the power of x multiplied by b raised to the power of x. So they share the same power, but the base are the different. Then you can multiply them together. This will equal to 1 minus beta t, and then raised to the power of negative alpha. So what we have is the moment generating function of the gamma random variable, where x following a gamma distribution with alpha and beta. Okay, so this is the MGF. And then again, the moment generating function can help us to calculating the moment. Okay, so just to summarize, what we have in the beginning is the arbitrary formula, is the formula for the arbitrary kth moment. So this formula gives us the ability to, when you plug in 1, k equal to 1, when you plug in k equal to 2, you will get the first moment and the second moment. And then here, what we're doing is using the definition of the moment generating function to get the formula of moment generating function. And this is the formula. And now we can also use the moment generating function to calculate the expected value and the second moment. Okay, so E of x, this is the first moment. And what we claimed last time is that if we want the kth order moment, all we need to do is taking the kth order derivative, set t equal to 0, you will get the corresponding moments. So this is the momentary function for x, for random variable x, and then set t equal to 0. Okay, so again, the momentary function is that, and then we need to take derivative of d with respect to t. So, first of all, let's bring the power to the front. We will have 1 minus beta t raised to the power of negative alpha minus 1. Okay, so the derivative of that is that you bring the power to the front and then minus the power minus 1. So you have that. But now you also need to take care of the chain rule. So if you take with respect to t, the first part goes to 0. The second part is beta. So now we're taking derivative with respect to t. So the chain rule gives us 0 minus a beta, which is just negative beta. Okay. Now let's group the thing together. So here we have a negative beta and a negative alpha. That means we have a positive alpha beta in the front. And then 1 minus beta t, negative alpha, negative 1. Again, we want to evaluate at t equal to 0. We will have alpha, beta, 1 minus 0, negative alpha, negative 1. So again, 1 raised to any arbitrary powers just equal to 1. So that is equal to alpha, beta. And then this is matching to our E of x raised to the power of k formula. Okay, so previously we derived a formula for the kth moment, and then we plug in k equal to 1 to get that powers. Right now we use the momentary function, and using the claim that we derive, we can see that we also get the alpha beta. So the first moment is here. Okay, so this is coming from the formula, and what we have here is coming from the moment generating function. Okay. Now let's take the second moment, and we claim that this is taking the second order derivative and set t equal to 0. Okay. Now let's evaluating this. So the first order derivative is here. Okay, so now this is the first derivative. Okay, and now let's take another derivative with respect to t. For this one, that means that's the second order derivative. Okay, so we have alpha, beta. Okay, so maybe I'll copy paste dt for that. So we need the second order derivative, but we already have a first order derivative. So I will just copy paste So that means we need to take another derivative of the first order derivative. So take another time. Okay. So alpha beta and then bring the power to the front. And then the power need to minus a 1 again, so we have a minus a 2. And then we need to do the chain rule, so again, this is 0 minus beta. Now we need to simplify it. So here we have alpha beta. Let me bring a negative sign to the front. That means we have alpha plus 1. Okay, so I'm just bringing the negative sign to the front. We'll also have 1 minus beta t, negative alpha minus 2. And then also a negative beta. So the negative sign cancel out. We will have alpha beta square, alpha plus 1, and then 1 minus beta t, negative alpha minus 2. And again, we have alpha square beta square plus alpha beta square, and then 1 minus beta t of alpha minus 2. But again, we need to evaluate at t equal to 0. So now, when we plug in t equal to 0, again, we have a 1 raised to the power of arbitrary power. That is still equal to 1. We have alpha square beta square plus alpha beta square. Okay, so this is the second moment from moment generating function. And now let's compare with this alpha square beta square plus alpha beta square. Okay, so again, this is matching from the result that from the arbitrary kth moment. So also matching with the arbitrary kth formula for the kth moment. Okay, so just to summarize, first of all, we introduced the distribution, which is called the gamma distribution, and then there are two parameters. So here we have the gamma for two parameters, we're referring to the distribution, and then gamma with one input is referring to gamma function. And here we have the probability density function for the gamma distribution, and then two properties. Okay. Although we haven't used the two, I guess. Yeah. And then here here's the definition of the gamma function. Okay. So this function input the alpha and the output the thing on the right hand side. Then we take a look and analyzing the integral of the numerator, where the numerator is called a kernel function. We use the U substitution. We find out that the integral of the kernel function is just the denominator. And here we also talk about that for any PDF that is a properly defined probability density function. If you're taking integral with respect to support, it will always equal to 1. This is kind of like in the discrete case, you sum over all the 6 for each side, that will give you a 1. So the probability for all the events is going to sum up to 1. Okay, so you sum the probability density function with respect to the random variable, you will end up with 1. And then here we provided the formula of an arbitrary kth moment, and then using that, the definition or the density will integrate to 1, we come up with this formula. So this is the formula for a arbitrary kth moment of the random variable. And then we plug in k equal to 1 to k equal to 2, we get the 2 moments, and the variance is alpha beta squared. And then what we did is that we calculate the moment generating function of the gamma distribution. Starting from the definition, the only difference here is that we're using the e raised to the power of tx. Again, using u substitution, we have our moment generating function. Okay, so the previous one is the formula for kth moment. The second one is the moment generating function of a gamma distribution. And then we use the derivative and the second order derivative set t equal to 0. We see that our answer is the same as what we get from the formula of the arbitrary kth moment. And then these are all the common and discussion for the gamma distribution.